Thanks, Rahul, for this opportunity. Very pleased to be here and um, to be introducing this topic to you, which is Bayesian networks for causal reasoning. Uh, just from my understanding, so how many of you here are clinicians? Okay, we have a few clinicians. Great. How many are biologists? Significant number. Okay, good. That actually helps. And I'm assuming the rest of you are quantitative, computer scientist, math, biology audience. So, am I too loud? Okay, good. So basically, Bayesian networks for causal reasoning is an approach, is a segue into making models that, as biologists and clinicians, we tend to make in our minds, right? So essentially, we look at a patient and we have lots of inputs about the patient coming in from various signals, right? So for example, what's their glucose, what is their blood pressure, what is their heart rate, and so on. And then we take some decisions on the basis of this kind of information. And it is known that a lot of this that goes on in a clinician's mind is actually very difficult to capture in linear models, right? So when we talk about models that are simple linear models or logistic regressions and so on, they tend to not capture all the complexities of biological and physiological phenomena. So the model that I'm going to introduce you to is just a starting point. This is not the end in itself. It is not the most advanced model. So that's a disclaimer that Bayesian networks are a good explainable AI approach to complex data sets, which will help you to reason with your data. Okay. And we'll come to, I'm not saying causal inference, right? I'm saying causal reasoning. And that's an intentional thing that I put in there, and I'll come to that later on. So what do we expect at the end of these 2 days? Okay, so today we have 2 sessions. In fact, one talk which will also introduce you to some of the work that we have been doing, the seminar talk. And tomorrow we have a hands-on about the Bayesian networks that we will conduct. But at the end of this, you should be able to conduct probabilistic reasoning with complex data sets. Complex data sets means not toy data sets that have a large number of variables with complex interdependencies amongst variables, right? Which may be non-linear. For example, the coupling between heart rate and blood pressure is not necessarily a linear coupling. Beyond a certain point, even if heart rate increases, blood pressure may not increase because it's a auto-regulated phenomenon, right? So you should be able to conduct probabilistic reasoning with complex data sets if the data sets have some interventions, right? Only if the data set has some intervention. For example, it's a known intervention in the form of, let's say, a clinician gave a drug, or you are doing a biological experiment and you actually in your experiment had an intervention, maybe of a drug intervention or some change that you had done. In that case, you can move from probabilistic reasoning to causal reasoning, but again with some limitations that I think may be beyond the purview of this particular 2 days. In the standard PGM course, which runs over a semester, we talk about all these details in a much elaborate manner, right? You should be able to build explainable AI models with Bayesian networks learned with a software called IISER, which is our own in-house software. You might have received a manual for that. We have tried to set it up for you, and just now I was trying some of the things. I think the IP that we have set it up on needs to be opened up, and I'll talk to Rahul about that. But we'll make sure that you are able to run these models by tomorrow. And then you can also conduct some level of decision making under uncertainty, which means we have probabilities, and then you can use those probabilities to conduct to achieve some decisions. Finally, if you think your models are good enough, you have validated your models, you have experimentally also conducted analysis and then basically validated, and then you can actually deploy your models as web applications. I mean, this is a plus. This is not necessarily something that is related to this course, but we have a functionality that, that you can also use. Recommended reading. I'm sure this today's 2-3 hours and tomorrow's is just going to be a teaser for you to actually go back. And if you develop interest in this, you probably would want to read these books, right? This is a very easy read, The Book of Why. It's by Julia Pearl. He is a UCLA computer scientist. He's a very well-renowned UCLA computer scientist who's worked all his life on causality. And this is another book, Causality, again by Julia Pearl. And why I like his books are because I subscribe to the way of causal reasoning, which basically he's a proponent of, and he's actually one of the pioneers of that line, which is probabilistic graphical models, right? Making things obvious through looking at graphical networks instead of making models that are more opaque. So Rosenbaum's models or Robbins' models are the other side of things. And then there's a book by Neil Friedman and Daphne Koller. Daphne Koller, again, a very celebrated scientist, was previously at Stanford, then with Google. And she also has a Coursera course by the same name, Probabilistic Graphical Models. So if you like what we discussed today, you would want to probably go back and look at the Coursera offering, which has much more detail of what we are going to be discussing. And again, if you want to dive into more details, I would recommend again this book by Julia Pearl, which is on causality, right? So you may be thinking, what is this causality that we are talking about, right? What is causality? I would like this to be a little bit more interactive. So do we know what do we understand by causality? Anybody would like to take a stab at what is causal? What is a causal model? Right.
So causality would mean that one action has led to another. So oftentimes we see two things are correlated, but that might not mean that one factor, but if one factor is the.
Perfect. So absolutely. So you, I think, used all the right keywords. So you've brought in, and this is a mistake that sometimes even the most advanced scientists also make, that if A is correlated with B, if I change A, B will also change, right? That may not be true, because correlations do not mean there's a causation, right? So it might just be a symptom of something that's lurking behind. And we'll see how do we get to that kind of reasoning, right? So, and causality means that we can determine that if I change this, this also should change, because they're causally or mechanistically, they are linked to each other, right? So in biology, when we are looking at models which are more mechanistic, associations can take us to a level which may be markers, right? But if we want to change something, you want to develop a different course of action for a patient, or if you want to develop a different course of action for a cell line, right? Or for the way a tumor would behave, and you might want to give a drug. You want to find mechanistic properties of the system, which will then lead to a change in the behavior, right? So that's why basically causality is important. And you brought in all the keywords that we typically think with correlations, right? And this is just, I would not have a lot of mathematical formulae in my slides, but this is definitely one that you would know. If you don't, I think this is a formula for sample covariance and sample correlation, right? You're just looking at how does one variable X change from the mean as another variable Y changes from the mean, right? So basically we are looking at covariance between X and Y, which are two variables, and we are seeing how does Y covary or X covary as the other one changes, right? What do we notice here? There's no sense of directionality here. X or Y, Y or X are interchangeable, right? Same with correlations. There's no sense of directionality in this. right? So that's why it is an association. Since it is this, we don't get a sense of if I change X, Y changes, but it also implies why I change Y, X changes, right? So that's why we don't want to get to that change argument with associations. And as I said, this is a mistake that we make most of the times, even in biology experiments, that we tend to use correlations for designing our experiments, which may be then flawed, right? So the difference between, as you know, difference between covariance and correlation is that you are normalizing covariance to basically get to correlations by the standard deviation of X and standard deviation of Y, which forces it to be within a certain range, which is -1 to +1, right? So essentially, that is how correlations operate. But as you said, correlations are not causations, right? So you can see that there may be a very strong correlation between X and Y, right? Or there may be a weak correlation between X and Y, but it does not mean X causes Y or Y causes X. Okay, so that's something that you have to keep in mind. Correlations have many other limitations. Okay, so this is a famous example from Enscombe's 1973 paper, where he constructed 4 data sets. You can see there's 4 data sets: set A, set B, set C, set D. These data sets are by design having the same mean of X and same mean of Y. Okay, if you look at the mean of X, the mean of X, mean of X, and mean of X, they'll all be the same. Same with the mean of Y. Not just that, they also have the same standard deviation of X and Y. This is by design, okay? So nothing is surprising here. But what is surprising is if you actually conducted a correlation test and looked at what are the estimates of the correlation value R, right? Pearson's correlation, you'll see that you'll actually see the same Pearson correlation in all of these. The regression line also is exactly the same. So R squared is 0.67. The regression line is also exactly the same, right? And Enscombe used it to reason that why looking at just some statistic, which is a value, and making inferences and taking decisions from that can be very misleading, right? Because unless you now it's moving. Unless you actually visualized what's going on at the back end, you would not know. So these are the 4 data sets. As you can see, this is how nicely behaved statistical linear data should look like, right? You can see there's some noise and Y and X are correlated, right? And it's a nice linear straight line fit. That's how we expect it to behave, right? And there's some stochasticities, there's some randomness around a line that you can imagine that's passing through the line of, passing through these points as a line of best fit. But here is another set, right? And you can see that it has the exact same regression equation because we are trying to force a line on the data which is curvilinear. It's not a line, it's a curve, right? So when you look at the line of best fit, it will achieve the same residuals, which is basically distances from the line of best fit squared, and then it'll have the same slope and intercept as well. But it's a completely different phenomena. We are trying to capture what is the phenomena, because when we are going towards causal models, what are we trying to do? We are trying to capture the phenomena that is generating this data. And I'm going to talk about that in my third talk today, which is generative models, right? And why that's important, that we are interested in understanding the mechanism, the mechanistic phenomena that are generating this data. And you can see that this phenomena is completely different from this phenomena. I'm not sure if you extended it, it might actually be a sinusoidal wave, right? And if it was a sinusoidal wave, and if you had a line of best fit, it actually would show zero correlation, and that's a different thing. But this is a different kind of a data generating process than this. Here, there's an effect of an outlier. It's a perfectly nice linear data set, but with one outlier, it actually skews your line of best fit towards that direction, right? Here is another extreme example with an outlier which achieves the same kind of outcome. So what the bottom line here is that we want to have models which don't just give us a single metric, which also are explainable, which we can visualize, inspect, reason with, and then go back to the bedside or go back to the bench and conduct experiments with, right? So that's the backend motivation. A more modern version of the Enscombe's paper is this paper from Autodesk that came out, I think, in 2014. And I have the link here. You can go back 2014 or 19. I'm not sure of the date, but but this paper showed that all these different data sets, which have now been generated through an optimization method called simulated annealing, have the exact same properties, just like the Enscombe's data set, right? So the same mean of X, same mean of Y, same standard deviation of X, same standard deviation of Y. The Pearson's R is 0.32. Okay, so it's a positively correlated data set. All of these different shapes are coming to the same correlation metric, which is this. Not just this, even this dinosaur here has the exact same statistics, right? But these are completely different, as you can see, completely different data sets, completely different phenomena. So again, a reason to basically visualize your data, visualize your models, right? So are there any questions so far? If there are no questions, we'll move forward. Yeah, so basically you can see that if you tried to force a linear fit on this data, it'll basically have the same correlation as before, right? So always visualize your data. That's one reason why moving towards Bayesian networks is a good case of achieving that good balance between having a model and having a visual interpretation of the model. The second thing that we would like to talk about is confounding. This is an example that I've taken from Julia Pearl's The Book of Why. I think I have a link in the following slide. I'm sorry if it's not here. This is just an example which basically shows that if you have data points, somewhat of a toy example, if you have exercise and cholesterol, and data points spread out like this. And this is actually taken from a real world example, but in this case, it's shown to be a toy example, right? And you are a policymaker, you're a health policymaker, you have this data, you're working for the Department of Health, right? You might actually give the wrong recommendation that more exercise leads to more cholesterol. So people should stop exercising, right? Which is, we know that's not true, right? So which means that there must be something more. There must be something more which is leading to this kind of an error in our reasoning. And that factor that is more is called a confounding factor, a lurking variable. If you stratified, and I think population geneticists know this, have known this forever, that we know that there's something called stratification. Something that may look to be reasonable for the entire data may be completely different if you stratified the data on basis of some factor, in this case, age. If you looked at age, this is age stratum 10, 20, 30, 40, 50. And if you had now stratified the data, you may see something like this emerge. That in each of these strata of the population, the line is actually now the opposite direction. It's not going like this. The line is going like this, right? So which means that there was a factor age, which when you used to stratify the data, gave a completely opposite picture. Does anybody know what is this called in statistics? Perfect. This is called Simpson's paradox, right? So yeah, so that's the link for this particular example on Julia Pearl's webpage. Another example that I commonly use. So in this example, basically you are now a air defense scientist, okay? And in the middle of World War II. And you're observing that you're working for the US government. You're observing that the planes that have come back from Germany have received hits at all these red points. And the government has asked you, where should I put more armor? Because you can't put armor everywhere. It will make the plane too heavy, right? So where would you put the armor? You can see the distribution of these red dots tells you where the plane was hit. So the question is, where would you put more armor? Reason. Wonderful. Absolutely. So yeah, so this is a very, this is a great audience. I think so basically the crucial piece of information that's missing here is that you're looking at the planes that have come back. And the planes that have come back have not been hit on the engines or in this middle part, right? So basically, again, if you just made a correlation, no, I should put an armor here, more armor here, because that's correlated with more hits, that would have led to a completely opposite decision, which would have been fatal again, right? So again, we want to get to these kind of inferences. Another example that I like to make, because most of the times we think that getting bigger and bigger data sets will alleviate some of these challenges, right? Which is not true, because in the age of, even in the age of big data, data generating mechanism is very important to be understood when we make models. So big data will not solve the problem of not having the right model. Please bear that in mind. Example, you are a manager in the bank, and there is a rule in the bank that the bank can give loans to people who are only more than 18 years of age, unless the person who is less than 18 years of age has rich parents, and the parents are known directly to the manager, right? It's an obvious rule that if you have to give a loan to a person who's less than 18 years of age, they better have rich parents, and the manager better know the parents so that they can actually retrieve the money. Now, a bank data set may be millions and trillions of such transactions, right? But if this was the rule that was injected in creating this database, I'm using the word injected here because it's a generative, we are trying to get to a generative model. What would happen is that in that database, all younger than 18-year people would have returned the loan because they had rich parents. So your model would say that give money, give loan to people who are less than 18 years of age, because they would have a high probability of returning, which is again a completely opposite kind of a conclusion that you would be drawing. So what do we want to do? We want to learn the generative mechanism. How did this data get generated? This data got generated from the planes that were coming back, right? And they got hit here. And you're making a counterfactual reasoning, which is not factual. You can't see that in the real world. Which is a counterfactual reasoning that you can infer with the model, right? And that's when you're able to make a counterfactual reasoning, that's when you can make a causal reasoning about the data, right? What would have happened in the other scenario? Final example, and then we'll go into the Bayes rule. I know this is slightly longer motivation, but would set us up for the following understanding of Bayesian networks. This is another example which you may be able to relate more with because recent, right? COVID-19 pandemic, Israeli data got published on COVID vaccine efficacy. If you look at the efficacy of the COVID vaccine in these subgroups of less than 50 and more than 50, separately, the efficacy is quite good, right? 91%, 85%. But if you look at the combined data together without stratification, 67% efficacy would give a wrong policy that COVID vaccination is not effective, right? So you want to learn what may be a confounding factor. Now the question is, can we learn what may be confounding in our data? And that's the motivation for the Bayesian network kind of model, where we would like to learn. We are building machine learning models. We don't know what may be confounding factors, right? Can we start learning what the confounding factors may be, or other factors maybe, which I'll come to later, which is the mediation and also the collision effects. But this is another reason that in today's big data age, where we won't be able to have reasoning or hypothesis on every variable. If you're looking at 30,000 genes, millions of SNPs, I don't know what is confounding in those 30,000 genes, right? So maybe we want to start moving towards models that can help us discover these phenomena. And that's why we are talking about Bayesian networks today. To understand Bayesian networks, let me actually, I think, draw how a confounding effect might look like, right? So which will come also in the later slide. So I'm drawing big so that it can be captured on the recording as well. So this is how a confounding effect will look like, okay? Let's say an X effect, a variable X that influences both A and B. Right? Now this is a motif. I'm introducing these terms which will become more clear. This is a motif. Why motif? You can see that if you had two nodes and if you only had a link between them, this is what we do in standard association networks. We have two nodes X and Y, and we have some correlation between them. Okay, it may be a correlation, Pearson correlation R is equal to, let's say, 0.7. So in an association network, a motif is only two nodes and an edge. In a Bayesian network, a motif is always three nodes and two edges, right? Why? Because now there's something fundamentally different between these two networks, and that is direction. I don't know who's saying that, but that's, thank you for that answer. That's in association, as we were discussing before, correlation between X and Y is the same as correlation between Y and X, right? But here we have no direction, right? I'm not using the arrow here, but here you can see that there's a directionality of this influence, right? And when you have directionality, you would see that two nodes having direction, and when you extend it to a three node, you will see three different motifs. This is called confounding. When the backend variable is actually influencing, and this is a statistical definition that we use in all biomedical statistics. When you're looking at correlation between X and Y, if they have a common cause, then they are confounded by that common cause, right? So we may have a spurious association. This is also called spurious association. Spurious association between A and B, which is coming from X, because X is the real common cause behind them, right? So if X increases, A also increases, B also increases, or whatever, because of which we'll see a spurious association between A and B. It will appear that as A increased, B increased, right? But actually it was the common cause X that was causing a change in both of these, right? So this is called confounding. Let me quickly draw the other motifs also. Again, 3 nodes. And this is called a mediation effect. So A, B, and C. So why we call it a mediation effect? Because B is the mediator of the effect going from A to C. So in a 3-node network, we are seeing that this kind of a relationship where a variable A, a variable B, and a variable C have this kind of A to B to C kind of a directionality that is called a mediation effect. And then there's a third motif, which is called a collider motif, which is the opposite of what you see here. Now you have 2 variables, X and Y, leading to change in Z. Again, something which is very common that's seen in biology, right? If you're looking at height, it's an effect of too many influencing variables, right? They lead to the same outcome change, which is happening in Z. So this is called a collider effect, collider motif. And this is also sometimes, I mean, it's very important. It's called intercausal reasoning. When we try to reason with these kind of structures, it's called intercausal. When you have 2 causes, cause A and cause B, right? And then if I know something about cause A, I can infer about cause B. I'll come to that in more detail later, but just bear in mind it's called intercausal reasoning. Intercausal reasoning. Now, why are these important? Why are we discussing these in today's? Because when we are trying to understand the mechanism of the mechanistic generation of data, these are the 3 motifs, key motifs that you would actually look at as they emerge in Bayesian networks. Either a variable A changes variable B, that changes variable C. That's called a mediation, right? Just bear in mind that if there is no change, if variable A changes and variable B does not change, given everything else, then they won't have a link at all, right? So there is some change, which means that there is some probabilistic influence flowing through the network, right? Similarly, variable X, variable A, and variable B, we are seeing that variable X is a confounder between variable A and B, and here X and Y are both influencing Z. Okay, any questions so far? We'll give examples of these in the coming slides. Yes.
Thank you. I'm learning a lot. So in your A to B to C model, what if A does affect through B, but also A directly affects C?
Wonderful. Thank you for that question. That is also possible. So you're saying A directly affects C, yeah.
Yeah.
So that is also possible. That is also possible, but that's a 2-node directed link. That's completely possible. So what would happen is that there's some influence that passes this way, and the goal of the network would be to partition a probabilistic flow along this and this, to come to an inference which is more faithful to the original, to the data, right? So this is completely possible, that you might have a direct influence also, but this can be learned from, and we see a lot of such examples. The idea would be how much influence flows in this direction, how much of this influence flows through the B. So that is the machine learning that happens in the network. But that's possible. Any other questions?
also account for the feedback loops, positive and negative feedback?
That's a great question again. So no, these are directed, I'm sorry, I did not introduce that term. These are directed acyclic graphs, right? So you are seeing in definition, by definition, they're acyclic. You can't have A to B back to A unless it is a folding in time. That is allowed, okay? But then you have to have time in your data, okay? So you can't learn from static data, you can't learn a feedback loop in Bayesian networks. These are directed acyclic graphs. Even in the dynamic graph, every static layer itself would also be a DAG, directed acyclic graph. It's directed, it would not have cycles, okay? Because then it gets into a loop, which basically is, it can't be solved for, okay? Yeah, that's a limitation of static Bayesian networks, that in biological data sets where you have a lot of feedback loops operating at the same time, these might be difficult to learn. However, there are approaches towards that. Time-based unfolding is one of the examples that that you can do, because even in biology, it's these two directions are not exactly the same always. Otherwise, it will be an equilibrium situation, right? So essentially, since there's an asymmetry, and if you have temporal information available, one direction is stronger at a certain time point, the other direction is stronger at another time point, that can be learned from data. Okay, yeah, great, good question. Any other questions? If not, then we proceed to what we have now, right? So we are looking at, so basically we were looking at these motifs and confounding effects, but the foundation of these, how do we learn these from data, right? This is easy to draw on a blackboard, but how do we actually learn these three kinds of motifs from data? You are a biologist, you have your gene expression data, you want to learn what may be these kind of influences in your data. And the basic statistical tool that we have is called conditional probability. I'm sure all of you know conditional probability. I'm just going to remind you what this helps us achieve. It helps us achieve a direction, which this association does not have. Because the conditional probability of A given B is not the same as conditional probability of B given A, right? The reference space is different, right? So that is the reason that you can actually calculate conditional probability of A given B and B given A and look at these differences, right? When you're saying A given B, you're having the same intersection space, but given B means that you're looking at the universe, you're looking at the space of B. So this divided by the space of B. Whereas when you're looking at B given A, you have the same numerator, but you have a different denominator. And this is a thing that is used very much in Bayes' rule. A very famous example is when we look at breast cancer detection using radiographs, and that's a commonly used example that's cited, right? So essentially, what conditional probability and Bayes' rule, which we'll come to shortly, allows us to do is basically leverage asymmetry of information, right? And when I say asymmetry of information, asymmetry means that there's a direction. They are not symmetrical. There is a certain direction in which I can draw an arrow, okay? So for example, if you're looking at a car and a wheel, I'm just making up this toy example, right? You're looking at a car and a wheel. If you observe just the wheel, what is the probability that the whole image was a car? It's different from what is the probability that if I look at the car, there was a wheel in the car. These two probabilities are different, right? So intuitively, these two probabilities, since they are different, they actually, the conditional probabilities of car given a wheel and a wheel given a car are not the same. So there's an asymmetry which is always there in the real world. which needs to be exploited using machine learning. That is what these allow us to do. But does that mean that car causes wheel? No. That's another point that I would like to just highlight, that please do realize and understand, because the next mistake that we make after thinking of correlations as causation is when we start imagining that these directions mean causation by themselves. They don't. Okay. From observational data, we can reason better than correlations, but we are still not there at causations. We need interventions for that. Okay. So, so please don't jump to the conclusion that car causes wheel. Okay. We are still not up the ladder of causality along this. So that's how basically, again, another example for the clinical colleagues here, aspirin and coronary artery disease, right? The probability of, you're looking at a table. That's what we as machine learning scientists would really get at the end of the day, a structured data. If you're working with structured data, a structured table where you're looking at, let's say, some treatments and some diagnosis of people, and then you say, oh, let's look at aspirin and coronary artery disease, right? So you'll see that the probability of aspirin in coronary artery disease may be different. I'm just using greater than from my own understanding, which may be wrong. May be greater than probability of coronary artery disease given aspirin, because aspirin is also given for other indications, right? So, but if a person is having coronary artery disease, there's a slightly higher probability that they may be on low dose aspirin. That's a standard guideline that's followed. Again, an example where we see that aspirin and coronary artery disease, they have a asymmetrical relationship, which we can then represent as a two-node directed with a directed edge kind of a motif, again, basically taking us beyond associations to more causal reasoning. And this is what we were basically discussing here. Mediation effect, A, B, C. Now, A is smoking, B is tar, C is lung cancer, right? So it's a mediation effect because we know that cancer happens because of tar that accumulates in the lung with smoking, right? So the tar is the real mediator. It's a real culprit, right? So if I somehow had some treatment which would remove the tar as a person would smoke, smoking would become independent of lung cancer. Does it make sense? That if we were able to remove the tar as it was getting accumulated in the lungs, smoking would not cause lung cancer. Increasing smoking would not lead to a change in increase in lung cancer, right? That's why it is an effect where if we condition on this, means when we were basically stratifying the data set by, let's say, a certain age. Here we are saying stratification of data within a certain tar range. If we know this, what is the value of tar accumulation within some, let's say, I don't know what the units might be, but within some range, right? Then this becomes independent of this. So the probabilistic influence, flow of influence stops if I condition on this particular variable. This is the next, I think I understand this may be somewhat complex, but please do ask questions. So what I'm going to repeat. What I'm saying is that in the real world, the flow of probabilistic influences that if there's higher probability of smoking, the probability of tar increases, which increases the probability of lung cancer, right? So just like electrical current, there is a flow of probability that is open, okay? But now if I fix this, whatever level, it may be low level, middle level, high level, then changing smoking will not change lung cancer. Let's say a person has accumulated 10 units of tar in their lung. They have accumulated some probability of getting lung cancer. Now I fix that by some treatment. So basically I condition that now probability is only 30%. I can't change that. What happens? Now changing this won't affect this. Changing smoking won't affect lung cancer in that scenario. Is it? I hope that's clear. So basically what is happening here is, if I condition on the middle node, the flow of probability stops. In other words, smoking becomes independent of lung cancer. Same thing happens when we have these three nodes like age, shoe size, and IQ. This is an example of a confounder. Okay. So if you don't have age corrected IQ, you'll see that as people grow, they accumulate more knowledge. So shoe size also grows. Age is the real cause behind increase in shoe size and IQ. If you were just looking at data, you might make a false, spurious conclusion, which we are showing here, that people with more shoe size have more IQ, which is not true, because if you corrected for age, which means you fixed the range of age within a certain age group, let's say 0 to 10, 10 to 20, 20 to 30, and so on. If you fixed this, these two become independent. If you did not fix this, that's why it is a confounder, right? That's why in statistics, we worry so much about confounders. That if we do not account for a confounder, if we don't fix this, we'll come to the wrong conclusion that shoe size increases IQ. Right? So basically, again, these two motifs share something similar, which is that the probabilistic influence stops when you condition on the middle node. These are the two nodes. This is the middle node. If I condition on this, this becomes independent of this. Shoe size becomes independent, unrelated with IQ, if I fix age. But if I don't fix age, I'm having a spurious. Here we don't have a spurious association. It's a different mechanism, but the influence stops. And these help us to basically, these flow of probabilistic influences help us to learn from data what may be the generative mechanism, right? Is a mediation effect hiding in the data for generating this particular, let's say, influence, or is there a confounding, or is there a collision effect, right? Which we called it as a collider motif, which is also called intercausal reasoning. Again, a famous example, if you went out and observed that the grass is wet, either it could have rained or the sprinkler might have been on. So there are two causes, either it rained or the sprinkler was on. Now, if you know that you now are observing this because you went out, you're observing the state of the grass, which is, say, let's say, which is wet, right? But if you now know that it had rained, will your belief about the probability of sprinkler stay the same, or will it change? It'll change, right? Because now you already know it rained, so the belief about sprinkler causing the rain would go down. Same thing would operate in the opposite direction. If you knew that the sprinkler was left on, your belief about the rain would go down. Only when you could observe that the grass was wet. If you're staying inside, you can't observe, you can't comment anything on the sprinkler and rain. You have to observe this, grass being wet. So this is an opposite effect from what we are seeing in these two. You're seeing when we observe the middle node, the probabilistic influence opens up. Knowing about this changes my beliefs about this. Right? This is called intercausal reasoning. Again, a very interesting phenomenon, both of interest to computer scientists and to biologists, because we often deal with these kind of data generating mechanisms where two causes lead to the same outcome. And we have to reason which one is playing out at this point of time, right? So what we've done so far, we have covered why correlations are not causation. They should be used very cautiously. Why we need directions, why we need the asymmetry of information to have these kind of directions and influences, why we need these motifs to help us reason, right? So now when you actually go back and when you build a model that's a Bayesian network model, you can start reasoning with it, right? You can't do much reasoning with correlation. What can you do with this? With an X and a Y, with a link in between. You can't reason much. But with this, now you can reason. There may be a mediation, or there may be a confounding, or there may be a collider or an intercausal reasoning. That's what we mean by probabilistic reasoning with Bayesian networks. Okay, we can observe and we can reason with such structures, which make sense to our intuitive understanding. Any questions so far? Yep.
Yeah, so my question is, are the number of edges either coming in or going out playing a role in specifying the node is of spatial importance? Like in all these three cases, either confounder or the mediator or the collider. So spatial importance is given to the node that is having the higher number of edges.
Yes, absolutely. So the question is that imagine, I might have some examples later. Imagine there are many variables that are looking like this, right? And then this is a network itself. There may be some edges pointing in as well, which is completely possible, right? So your question is that this particular node, for example, if I look at this side of the network, left-hand side, this particular node has a lot many edges coming in, right? And there may be some going out as well, right? And then is this node more important? Should we give more importance to this than maybe this node?
Yes.
The answer is empirically, yeah, empirically speaking, yes. Why? Because if we actually, it is actually summarizing a lot of probabilistic influence in this part of the network, a lot of probability flow. Imagine this as a current flowing, right? A lot of current flowing in from a lot of influences, right? And then going out here, and then this current passes on somewhere here as well, and then this is linked. So if we are looking at these two sides of things, and a real world example that I can use from our own work is antibiotic resistance. So there may be many antibiotics that we are observing being used in the real world, but there may be one particular antibiotic, right, which actually summarizes a lot of what is happening in resistance. And that is important to what is happening in the clinical situation, which may be on this side, right? Clinical outcomes, let's say. So yes, we do tend to look at these nodes as having a lot of, as being, let's say, the integrator of a lot of probabilistic influence that is flowing in the network. So they are important. In association networks, we call them degree centrality and so on, that how many edges are is a node connected with, that's a degree centrality measure. So yes, centrality measures in Bayesian networks are also important.
Thank you.
Yep.
What is the meaning of motif exactly?
Motif is just a structure, right? So motif is a building block, right? So it is just a building block of a network, maybe thousands of nodes. But any network, a Bayesian network, right? Any network with a directed edge, the building block of the network with even with thousands of edges will be a simple three node 2-edge motif. That's like a building block which allows you to do reasoning, right? I mean, the building block is even smaller. You can think about this as A and B, and they have a directed edge. But it doesn't help you reason much beyond this, right? You can't do higher order thinking with this. It just is telling you there's a asymmetric relationship between A and B. If you had to do some higher order thinking like confounding and mediation, and the building block is a 3-node structure, right? Beyond that, it's difficult to actually conduct any higher order thinking as well. Okay, so that's why for reasoning purposes, these are the building blocks. That's the meaning of a motif.
Yes, sir. So my question is that when you draw these motives and draw inferences, is like prior information regarding the knowledge is important, or can you infer some information just looking at the
Great question.
network?
You're setting it up for the next part of the lecture, which will happen after lunch. Exactly, you can account for prior information. In Bayesian network models, there are two steps to, actually more than two, but the two basic steps to learn the model are learning the structure, which is exactly what we have been looking at, that what is the motif structure of the behind the data. And then of course, parameterizing it and then inferring it, in conducting inference with it, right? So prior information is very important. If there is a known, for example, you know that A cannot influence B. In your domain, through your domain understanding, if you know that A cannot influence B. Right? For example, things which are prohibited, going back in time. Okay, so if there's a temporal influence and so on, or if you know that something is completely not making sense in the medical or biological sense, you can actually prohibit this structure at the time of learning. And we will see how does it happen. It's called blacklisting and whitelisting of variables. So you can prohibit this link to be formed. This is one example where you can inject prior knowledge about how variables may be linked. Okay.
Hello?
Yeah.
And sir, if you do not have that biological
You can still start
information,
from scratch. Okay, so you can still start from scratch and learn the structure and look at it. And you may have heard about transfer learning and pre-trained models, which have become very popular now with large language models and GPT kind of models, right? Where you can train on Wikipedia data, transfer that to clinical data and learn. You can still do that with these kind of models as well. Because why? Because once you have learned a structure, let's say for a hospital, let's say AIMS, New Delhi, with antibiotic resistance patterns and so on, you know what is the directed acyclic graph for that particular influences. Now you can take that structure, same structure to, let's say, Safdarjung Hospital, New Delhi, okay, which is right across the road. That exact same model may not apply. It's a different setting, but it gives you a prior to learn from, which you can then basically improve with the Safdarjung data, right? So there is, since these are generative models, just like large language models, are also another word for these are representation learning models. Like PCA, these models learn the representation of data, I mean, the generating mechanism of data, or the joint probabilistic distribution factored into marginals. And so basically what it allows you to do is to take the model as a representation and then use that in another setting and improve that model. That is also possible, that if you don't have something to start with, you learn from scratch. You take it to a setting. If it does not work well, you can actually improve it using the current data, right? But obviously you need some data to start with, even if you have no priors. So we only have 5 minutes before lunch, but let me see if there's something crucial. Any other questions? Yeah. Yeah.
I think it's not. So you have discussed a lot about the directions. Do we also consider about the magnitude of those probability or the amount or the size of the confounding? So for example, if there is a confounder, but the magnitude is very less, so do we need to more worry about that, or we need to consider, we need to look at other confounders, which may be the very strong confounders, right?
Absolutely. I mean, what you've just said is correct,
Yeah.
that the network will tell you whether, with some level of confidence,
Yeah.
which we will see how we can arrive at through bootstrapping and so on, with some level of confidence, we can infer that there is a, let's say this link. or this link, right? This confounding link, right? But then this variable A, B might also have some other confounder, which may be a stronger, right? So, but then this edge strength will be weaker here and stronger there. So, but what do you do with that is your decision. You can set thresholds that give me all the effects which are beyond, let's say, I typically take 51%, which is majority voting, right?
Okay.
If I build 501 networks, have majority of networks voted for this particular edge or not. But then after I've chosen a threshold, it's up to you to whether to keep it or drop it when you are having another situation with another confounder. So obviously you need to worry about the stronger confounder, right? But that's up to you. It will give you the strength of link that you can see here.
Okay, thank you.
Sure. So I think, let me see if there's something directly connecting the next section. No, I think perfect. So this is a perfect stop point because now we go into Bayes rule after the lunch session, and then we will also look at some hands-on examples, and then basically tomorrow we have a hands-on. There's a housekeeping announcement. I'm not sure how many of you were able to install the IISER software from GitHub. Can you have a show of hands if you were able to install? Wonderful. So we have at least a few who were able to install. Windows, Linux systems, what systems do you have? Linux. Windows? Windows at the back? So mostly Windows systems, okay. We have a Docker image also, okay. So basically we anticipate because it's a slightly large software with a lot of dependencies, and R keeps on updating some of these dependencies. So sometimes some installations fail. Did you try launching IISER and did it? Okay, great. So if it is launched for you, the dependencies have been installed correctly. If it is not launched, then some dependency issues are maybe there. But for others who are using Linux, we have a Docker image, which is basically an environment that you can directly use in your system if you have Linux, and it'll work out of the box. There's a third option that is expected to be our primary option. We have set up on our own server at IIIT Delhi accounts for all of you to access our IISER installation there and our Docker image there. I tried doing that yesterday and this morning. It looks like ICTS has blocked some of the IPs. It's working now. I think so. Our IT system connected with them. Okay, so good news, which means that no installations might be needed. I'll just make sure that it's in place. So you all should be able to log in into our server and run the hands-on without any installations as well, hopefully, and we'll check that and confirm. Thank you so much, and we'll meet after the lunch.